Hello student, very good morning to all of you. How are you? I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think we were discussing about the polysaccharides. So polysaccharides, and as we know that polysaccharides are formed by large number of monosaccharide unit, or it is a polymer of monosaccharide unit. That type of the introductory part we have seen, we have discussed in our previous lecture. So in that we also discuss, in addition to that we also discuss, that is a oligosaccharides. They means the disaccharides. Disaccharide means after the hydrolysis we are generally get two monosaccharide units. So there are three main disaccharide we have discussed. One is sucrose, another one is maltose, and third one is lactose. These are the three disaccharide we have seen, their structure, as well as we also discuss which of them exhibit or shows reducing sugar properties or non-reducing. If you remember the previous lecture, you can easily find out the reducing property and the non-reducing property of that sugar. Generally is only one trick you should remember. Those disaccharide exhibit hemiacetal structure, they shows the reducing properties, and those that does not contain hemiacetal group, they are the non-reducing sugar. And if you observe the structure of sucrose, you will find there is no hemiacetal group present. Therefore sucrose is a non-reducing sugar. Similarly, if you observe the structure of maltose and lactose carefully, you will find the anomeric hydroxyl group is not involved in the glycosidic bond formation. It remains as it is, means the hemiacetal group present in maltose as well as in a lactose, and therefore maltose and lactose are reducing sugar. So that the simple thing you must remember. And then I think today we are going to discuss very important point as far as carbohydrate chemistry is concerned. In my previous lecture I already told you that why it is important, because it has a special characteristic, or what we can call it as a special feature, important feature, or it has very important significant as far as this carbohydrate chemistry is concerned, because those are students want or will to achieve their higher study and interested in a research, those wish to become the scientists in future, they will have great opportunities in this field, because it is a very challenging field as far as research point of view is concerned. And therefore if you study, if you if you focus your attention toward the basic of carbohydrate, as well as this is a advanced version of that carbohydrate, that is a recent or upcoming research point of view, it's very important why the university introduced this topic at this level. The reason behind it is very clear, because university as well as the higher study now onward is becomes as very challenging due to the modern technology. You have to adopt it and try to do the quality research, and that's why university introducing such type of challenging concept or the subject at this level, so that the student should get aware of such type of the concept, and if they are find interest, if they know the how this, because carbohydrates chemistry is naturally carbohydrates are present if you talk about as a raw material, is easily available or readily available, and you have to design the process or the new methodology or a novel work in this field. It is challenging field, and that's why today we are talking about the synthesis of glycosides, how the glycosides are formed, or the glycosidic linkage, how it is formed, and what will be the actual glycosyl donor-acceptor concept similar to us, because whenever there is a reaction is to occur, there require or it need one must be donor and one must be acceptor. Then and there will be the formation of new bond or the formation of new linkage, generally as a glycosidic linkage, and therefore, and when the new bonds are formed, this is happen or this is takes place due to the nature of these two concepts. And if you see here, a donor means which can donate the lone pair and one should accept that lone pair. And when it will happen, donor means it must have a ability to donate. When it will donate, if it has the excess number of electron or number of whatever property it possesses, then and then it can donate. And the acceptor means what? When it will accept when there is some deficiency in that, then and then one is needed and one is required. So there is a give and take. That type of the tendency of that molecule get collide together and the form the structure, and for this concept is known as a glycosyl donor-acceptor concept. One is a giving, means a donor species, and one is accepting, that is a acceptor species. And when these happen, there will be a formation of the glycosidic linkage or the glycosidic bond, and that's why this concept, by using this concept, we are going to start or we are going to discuss the general method for glycosyl bond formation. When that bond is formed, when that linkage is formed, when there is a one species can donate and one species can accept, then and then that type of the things is happening, and you will get as a new different type of the. And one more thing you should remember, when one is a donor and one is a acceptor, there must be as a chemoselectivity. Then as we know that when hydroxyl, and specifically we are talking about the anomeric hydroxyl group. Let us see the simplest structure of the D-glucose. And D-glucose, when a ring form is formed, and that ring form generally we are considering here, that is a most stable form, that is a chair form, Paranose ring type of the concept. And according to as a Haworth projection formula, when that glucose acquire the ring structure, it forms two ring structure. One is called as alpha, another one is called as a beta form. Alpha form means what and beta form means what? That is depending on the anomeric carbon atom. As we know that anomeric carbon atom, it is a carbon atom of when there is a ring formation takes place, extra chiral center is generated over there, or the formyl carbonyl carbon. If you see that open chain structure, if you imagine the open chain structure according to as a Fisher projection formula, there you will see the formyl group is present, and that formyl group is a very potential where the reaction can occur. And when according to the other things like as a thermodynamic concept or the kinetic control, whatever concept you have to use over there, then the reaction takes place between as a formyl group, because it is a very potential, and the hydroxyl group at carbon number 5, they are forming as a ring. There are two possibilities are there, and that OH can goes above the plane or can go below the plane. When it comes above the plane, that form is called as a beta form. Those anomeric carbon atom goes below the plane, that is called as a alpha form. And all the other bulky group, generally in this case all the hydroxyl group prefer to stay at equatorial position. And remember the chair form of that conformation, those bulky group prefer to stay at equatorial position. But in this case, the hydroxyl group which is present at alpha position, it is what we can call it as a, it is a less stable. Generally we are getting as a alpha form is a 38%, whereas beta form is a 62% we are getting. Why 62%? Because all the bulkier group they are lying at equatorial position, and therefore there is a no 1,3 what we can call it as a non-bonding to sigma, anti-bonding sigma interaction is not present, and therefore that beta form is a more stable. If you observe the structure carefully, you will find all the hydroxyl group as well as one primary alcohol group which is lying at equatorial position, and therefore beta form is a major than the alpha form. That alpha form, look at in the alpha form, hydroxy group at an anomeric carbon atom which is present at axial position, and it generate or it create the 1,3 diaxial interaction. And as we know that 1,3 diaxial interaction, due to that crowding or that interaction, internal energy increases. Once the internal energy increases, stability of that molecule goes on decreasing. Remember, the energy and the stability, they are exactly opposite to each other. Means internal energy increases, stability gradually goes on decreasing. Or if the internal energy is lower, the stability gradually goes on increasing. So that's the relation. They are inversely proportional to each other, and that the concept we are going to use in this here today, that is a glycosyl donor-acceptor concept. And when there is a formation of O-glycosyl, O-glycosyl means that oxygen atom, that's why it is referred as O-glycosyl trichloroacetimidate. So that type of the here is written as a trichloroacetimidate. This is a one of the what we can call it as in anomeric hydroxyl group. It need whether activation or deactivation, and generally for activation or for that purpose we are generally using the concept trichloroacetimidate. At an anomeric carbon atom, we are introducing one very prominent group where it can be reacted. It is act as a donor, and on another unit of that sugar unit, and form as a glycosyl bond, and the new compounds are formed. And therefore this is essential to remember O-glycyl trichloroacetimate have proven to be valuable glycosyl donor. As I already told you that glycosyl bond, how it is formed, that becomes as a donor for efficient synthesis of various types of glycosides. Glycosides means two monosaccharide units is combined together with that glycosidic bond formation takes place. But how it form, why it form, how much is the time required, whether it is stable or unstable, so that type of the thing we are going to learn over here. So here there is of formation and their high glycosyl donor properties releases under mild acid catalysis has led to extraordinary wide application. Not surprisingly, O-glycosyl trichloroacetimidate have often afforded the best result in demoliding glycosylation studies. The trichloroacetimates method will therefore continue to advance efficient synthesis, particularly for the complex glycoconjugates, and which are in demand for biological and clinical studies. And therefore these, and at the beginning I already told you that why this glycosidic synthesis is important, because for the biological as well as clinical studies it is very important. And therefore we are just starting how we can, before that we are discussing the introductory part regarding that, because as the day goes we will study differ in this particular field, and we will understood the actual concept of that O-glycyl or the glycosyl donor acceptor. And for biological and clinical studies, thus the trichloroacetimidate method will also contribute strongly to the future development of glycoscience. So here let us see glycosylation with thioglycoside donors. That is also as another concept we will study in detail, but the stability of that thioglycylation was also their very mild conversion into glycosyl halides. Hence thioglycosides were initially used as a convenient precursor for various glycosyl halides, and which then could be used as a donor in glycosylation reaction, that we will see again later. Later it was found that glycosides could be activated directly by the use of chemoselective through thiophilic promoters, and this discovery opened up a new field of applicable donors and glycosylation reaction. So trichloroacetimidate, what does it mean, or the general method for glycosylic bond formation, that concept we are discussing right now. So glycoside bond formation generally requires activation of the sugar at the anomeric center. As we know that anomeric center only differ the anomers means what, the optical isomers or the diastereomer, they differ at only one configuration, at only one configuration, and therefore it is known as anomers. And to this end, activation through anomeric oxygen exchange reaction, the classical Kinning's NOR method and its modification, sulfur based activation, etc., or alternatively activation through retention of the anomeric oxygen, trichloroacetimidate method, phosphate and phosphate activation, etc. It has already become a classical method, and this is essentially because only catalytic amount of promoter are required to provide very high glycosyl donor properties, whereas the anomeric oxygen exchange based method generally require at least equimolar amount of a promoter system, and which is obviously often associated with disadvantage of various kinds. The basic principle of trichloroacetimidate method consists in a simple base catalyzed addition of trichloroacetamide to the anomeric hydroxyl group to generate the O-glycosyl trichloroacetamate. Let us see here how the reaction trichloroacetamate can be formed over there. As we know that this is the general scheme I am going to represent over here, oxygen atom, and here this is the this triggering type of the bond. It indicates that this hydroxy group, this type of the arrow indicate that this hydroxy group, we don't know whether it is above the plane or below the plane. So that is the meaning of that, and this is a thick line indicate that this is projecting toward us, and all other bonds are lying in a equatorial position, that is shown over here like this. Other hydroxy groups I am showing like this only. So that is the general representation of that what we can call it as a glucose, right? D-glucose. We don't know whether it is that hydroxyl group. This is an anomeric carbon atom, right? At anomeric carbon atom, it is responsible for the other reaction, and that's why I am showing you. And as we know that this shear form at an equilibrium is as a base catalysis. What is going to happen here? Base catalysis. In the base catalysis, what is going to happen over here? It can be donate that hydrogen atom. Hydrogen atom is displaced over here. When hydrogen atom is leaving, it leaves its bonding pair along it, and therefore we are going to get over here. Let's see how we are going to get over here. We don't know that oxygen, when hydrogen atom is detached from here, the negative charge comes on that oxygen atom. Now it becomes as a anomeric, as a more donor over here. I am showing this is a thick line that are projecting above the plane or is near the, and now here whatever other hydroxy groups are, they are lying equatorially, and that is showed like this. And now when that type of the alkoxide type of the things are present over there, so we can show over here this bond. One is a very small arrow I am showing, and one is a very means the possibility of that and anomer is not what we can call it as a, here we can draw this type of the arrows. Then here we can draw this one C double bond O and H. Here you can show that hydroxy group, one hydroxy group here, another hydroxy group over here, and here we can write this oxygen atom and negative charge present on it, and this is showing in the square bracket. Look at how this ring get open form as this type of the thing, but that is not observed. Reaction with this is a reaction with trichloroacetimate not observed. Trichloroacetimate. This is the structure of trichloroacetimate, Cl3C and cyanide group, 3 chlorine group attached to that, and that's why it is known as a trichloroacetimidate. The structure of that is this one, Cl3CCl. So that is the structure of trichloroacetimidate. This is known as a Cl3C and Cl. This is the structure of trichloroacetimate. And now in here I am showing this again as a equilibrium. At an equilibrium, it is a base over here, and the ring get open, and this will be this Cl3C. Then what we can call it here, C double bond O, C double bond O. This is a amide, trichloroacetimates further converted into here is water, elimination of water. We are going to get here Cl3C and Cl. This type of the compound we are going to get over here, right? So this is the compound which we are going to get over here, and after that here mild acid catalysis. Here is a mild acid catalysis is used over here. And after using that mild acid catalysis, this one, mild acid catalysis, that is here alcohol is used, OR, and then that is, this is a scheme number first is shown over here, and here you are going to get this structure once again. Here we do not know what is that, but here double bond NH, and then here will be CCl3, that structure. Another thing, this remains this ring as usual, but here this is hydroxy group equatorial position, this is at equatorial position, and this is also at equatorial position, all these things, and it can be, or here you may get this type of the compound O, then this one, this OR, then other things are remains as it is. Here is a, what is that, this one, then this, and then there will be a this one, sorry, not this one, this is the thing, this is a scheme number first, this is a scheme number first, CHEM, this is a scheme number first, represent how the trichloroacetimidate structures are useful here for this reaction. Now let's see here, this reaction is generally high yielding, and because of its reversibility, high anomeric control can often be achieved. In addition, competing reaction with non-aromatic hydroxyl group are not observed. So in the second step, under mild acid or Lewis acid catalysis, glycosylation of various nucleophiles, for instance of alcohols, etc., can be readily achieved in general. High yield and high anomeric control are obtained, and that's why the anomeric control is derived from the glycosyl donors anomeric configuration, inversion or retention from enchimeric assistance from the influence of the solvent or from thermodynamic or kinetic effect. And this is the method now. The reported method for the formation and the reaction of trichloroacetimidates are well established. Use of sodium hydride or cesium carbonate as base for the reaction of 1O unprotected sugar with acetonitrile Cl3CCN yields generally the thermodynamic. This is not the structure of this. So this is the trichloroacetimidate, that is a for it is generally converted into as a trichloroacetonitrile. This is a structure of trichloroacetonitrile, yield generally the thermodynamically favored O alpha glycosyl trichloroacetimidates, and whereas use of potassium carbonate K2CO3 yields O beta glycosyl trichloroacetimidates because of kinetic reaction control, and use of 1,8-diaza bicyclo 540 undecayed 7-ENE DBU often yield alpha beta mixture, mostly favoring the alpha trichloroacetimidates. Recently, application of new base system has been reported using 7-methyl-157 triaza bicyclo 440 dec 5-NE MTBD or phase transfer catalysis 50% KOH dichloromethane tetra N-butyl ammonium hydrogen sulfate, which yield exclusively alpha trichloroacetimidates in very good yield 96%, beside the well established catalyst for glycosylation reaction with trichloroacetimidates. Some new catalysts have been investigated. the use of silver trifluoromethane sulfonate in the reaction with thalidomide-protected glucosamine trichloroacetimidate gave higher yield and smaller amount of alpha glucoside than the use of boron trifluoride etherate, and this procedure also avoid acyl migration in the acceptor molecule, but stoichiometric amount of the promoter are required. And use of lithium perchlorate in dichloromethane require a large excess of promoter, but with lithium trifluoromethane sulfonate only 0.05 equivalents are required. Both catalysts give high yield, but the alpha beta selectivity is low and has to be improved before general application is possible. The synthesis of other O-glycosyl immediate, that is O-glucopyranol, dichloro, these are under investigation. Thus variation in reactivity selectively are expected. This, I think we have talked a lot about this one, that is glycosyl donor-acceptor concept, or the general method for the formation of the glycosylic bonds. So remaining part we will see tomorrow. Let us stop today here. Thank you. Have a nice day.